Welcome to the ratio test for convergence. So the test says that if the sequence a sub n is a positive sequence, then the series, that is this sum from n equals 1 to infinity of a sub n, converges if the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to a value less than 1. So in other words, if the limit of a sub n plus 1 over a sub n exists and is less than 1, then the series converges. It diverges if the limit as n goes to infinity of a sub n plus 1 over a sub n exists and is greater than 1. And if the limit is equal to 1, then we can't tell one way or another. So if the limit as n goes to infinity of a sub n plus 1 over a sub n equals 1, then the series may converge or diverge. So in this case, you will need to use a different test. So understanding the test. So essentially, if the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1, that means we can pick r r less than 1 should be between 0 and 1, right? Such that a sub n plus 1 over a sub n is less than or equal to r for large n. So what that means then is that a sub n plus 1 is less than or equal to r times a sub n for large n. Right? And so essentially, we would have, say, our a sub n, and then a sub n plus 1, we know is less than or equal to r times a sub n. And then a sub n plus 2, we would know would be less than or equal to r times a sub n plus 1, which would be less than or equal to r squared times a sub n plus 1. And so essentially we get each of our terms is less than or equal to r to the k times a sub n plus k minus 1. oops, sorry. This should have been, the last one would be r squared, a sub n plus 2 is less than or equal to r squared times a sub n. And we can just go r to the k times a sub n for that n plus kth term. And so what we get then is that essentially the sequence acts like a geometric sequence towards the end, right? Or the sequence is sort of tracked below a geometric sequence. With absolute value of r less than 1. And so we have convergence. Similarly, right, if the limit as n goes to infinity of a sub n plus 1 over a sub n equals L larger than 1, right? Then we can find, oops, we can find k greater than 1, such that a sub n plus 1, actually, let's just use r, we don't need to use k, such that a sub n plus 1 over a sub n is greater than or equal to r for large n. Right? Then we have a sub n plus 1 is greater than or equal to r times a sub n. So that would mean a sub n plus 2 is greater than or equal to r times a sub n plus 1 is greater than or equal to r squared times a sub n. And we could continue this down to a sub n plus k is greater than or equal to r to the k times a sub n. Right? So once again, our sequence behaves like a geometric sequence. So essentially the a sub n's are trapped above a geometric sequence. With absolute value of r greater than 1. Right? And when we have that absolute value of r greater than 1, then we have divergence, right, for our geometric sequence. And so we get that our sum from n equals 1 to infinity of a sub n diverges in this case. Right? So essentially, this ratio rule kind of behaves just like, it kind of shows that the series behaves like a geometric series. So if that ratio limits at something less than 1, it behaves like a geometric series with r less than 1, between 0 and 1. And if that ratio goes to something larger than 1, it behaves like a geometric series with r larger than 1. So that is sort of the idea behind the ratio test. In the next video, we will go ahead and actually apply the ratio test.